Okay. Well, thank you for joining us today. Today, we're going to be hearing from Dr. Rasoul Sorkhabi. He's going to be presenting on deepwater superbasins. At the end, Rasoul, if you want to answer some questions, it's always a good idea for people to put their questions in the chat function. And then that way Rasoul can read them at the end of the webinar and go through them. So with that, here's Dr. Sorkhabi on deepwater superbasins.
Thank you, Jennifer. Okay, let me share my screen. Can you see my screen, Jennifer?
I can see it, yes.
Okay, wonderful. Okay, well, thank you all for joining this EGI webinar. As Jennifer mentioned, my name is Rasoul Sorkhabi. I'm a research professor at the University of Utah's Energy and Geoscience Institute, and I'm going to share some thoughts about deepwater superbasins, the discovery trends, and also some future potential and prospects. I am sure most of you are familiar with EGI, but for those of you who have not visited our institute in Salt Lake City, so I will start with a little bit of local geology. So we are located really at the boundary between the Rocky Mountains and the Great Basin Range. So we have access to both, I would say, compressional tectonics as well as extensional tectonics. And actually, the Great Salt Lake is a tectonic basin, and this is probably one of the earliest extensional basins formed, probably in late Oligocene in the Great Basin. So if you have not visited EGI in Salt Lake City, please plan to do so. It's a great place for geology. And this is a view of our building in the research park of the University of Utah. Now, this slide is a kind of a crystal ball, our crystal ball, or I should say a landscape map for the oil and gas industry. I have divided their activities into four areas: deep water, shale, mostly in North America, natural gas. These three areas are dominated by international oil companies. They do most of the exploration and marketing. They have access to most of the market. Also, traditional onshore operations are mainly done by relatively small companies, especially in the US. National oil companies are a bit different because they have they are limited, or they are more interested in whatever they have in their backyard. So globally, they have most of the reserves, I would say, and also they produce a lot. Now, the entire oil and gas industry, I would say in the post-COVID years, it's going through a transition. The goal is to really do massive decarbonization and also development of renewable energy sources as a pathway for energy transition by, let's say, 250 or so. Having said that, right now, the revenue source for all oil and gas companies is exclusively or mostly oil and gas production and sale. So in the past year or so, there have been some interest on the part of these companies to grow their oil and gas reserves so that they are financially in a healthy position uh, for both their stakeholders as well as to have financial resources for energy transition. My focus is on deep water um, offshore operations. So I'd like to put this space in a historical context. So probably the oil industry, the oil and gas industry has gone through four waves in the past since the mid 19th century. So the first wave was onshore, which is still continuing. It started in 1860 in Pennsylvania. Then around 1950 or so, the oil industry moved offshore, especially in the Gulf of Mexico, first shelf. And since 1995, deepwater has become a very important space for oil and gas exploration globally, I should say. And in the past 15 years or so, the shale revolution has added another wave of petroleum exploration and production. Now, each one of these petroleum waves was made possible by really technological developments. In the case of offshore, shelf, and deep water exploration, ocean floor mapping, especially in the 1950s and 60s, was crucial. At that time, geologists could characterize, could map not only the coastal areas, but also continental shelf, slope, turbidite sediments, continental rise sediments, and the nature of the oceanic floor and oceanic crust. Well logging and seismic imaging have also been very important for offshore exploration, as it was for onshore exploration. And also the drilling technology has advanced tremendously. I mean, today, the oil companies can access water depths of 3,000 meters, 12,000 feet, and then drill some of the deepest wells, let's say another 3,000 meters below sea floor. So this technological advances have been very important and really phenomenal in the history of oil and gas industry. Now, when I say deepwater superbasins, so let's do some terminology, some definitions. What are superbasins? For those of you who have worked in the oil and gas industry, you are familiar with very traditional oil field classification based on recoverable reserves. So we have minor fields, major fields. Giant fields are those which have recoverable reserves of more than 500 million barrels, and then supergiants have more than 5 billion barrels. And these two categories, giant and supergiant fields, are sometimes called elephants. And since 1970, AAPG has published a series of memoirs basically describing the giant fields of the past decades. The last memoir came out 2 years ago, I think. Most of these volumes and memoirs are available at AAPG website for purchase. Now, with the shale revolution, this term superbasin was introduced, especially by IHS. And AAPG organized, hosted a series of conferences. I attended some of them. They have also published 4 special issues of AAPG Bulletin, um, really focusing on superbasins. Now, the definition that IHS and the AAPG publication have offered for a superbasin is the following. Those basins which have already produced 5 billion barrels of oil, they still contain another 5 billion barrels. There are several plays, at least one or, I'm sorry, at least 2 or several petroleum systems present in the basin, and also substantial infrastructure for development. So this is the definition that IHS and the APG publications have offered for superbasins. This particular map comes from an AAPG publication by Charles Sternbach. He edited almost all those. It was a co-editor for those 4 AAPG Bulletin special issues. On this map, the main idea is that even though we have almost 1,000 sedimentary basins, but really 23 onshore and 8 offshore super basins, they dominate the world oil production. And also in terms of giant fields, 60% of them are located in only 5% of the super basins. Post-COVID, last year, Wood Mackenzie revised this concept of super basin, and they introduced what's called energy super basins. And this particular diagram comes from Wood Mackenzie. Basically, the idea is that rather than simply focusing on oil and gas resources, energy super basins also try to tap into other energy resources present in the same super basin for generation of electricity, and also do carbon sequestration in the same super basin. So it's a hub, energy hub for hybrid production and also decarbonization. Woodmac, they listed 44 traditional super basins, which contain 90% of world's oil and gas proven reserves. And of these 44 super basins, 16 of them are located offshore. Now, at EGI, especially this year, we are starting a new initiative, what we call Deepwater Energy Superbasins, more focus on offshore rather than onshore. And I will share a few slides, basically sharing our thoughts. Well, for one thing, 72% of the Earth's surface is covered with water, not land. And offshore basins, especially along the continental margins, you have thousands of meters of sediments, tens of thousands of feet of sediments accumulated offshore. So it is a huge playground for exploration. Really relative to its potential, deep water basins are underexplored, I would say. This particular table shows the number of wildcats drilled in 2021. As you can see, 423 wells were drilled onshore and only 221 wells were drilled offshore. But even then, the success rate for offshore wells were slightly higher. There are several maps which depict the greater potential of deep water basins. Um, in fact, most of these deep water basins are really unexplored, relatively less explored. Um, and in terms of production, this particular map um, coming from Eventbrite, it's a stock company. Most of the production uh, producing fields compared to the size of offshore wells is relatively small. So there is huge potential for offshore um, exploration, deep water exploration, and also finding really huge reserves, as also shown on this map by Baker Hughes. Um, this diagram shows the break-even oil prices, and there are some interesting takeaway lessons. Well, obviously, onshore Middle East oil um, is really the production cost is some among the lowest in the world. And then the offshore and deep water break-even oil prices are actually lower than shale plays. Even deep water, ultra deep water, like $57 a barrel relative compared to $62 per barrel from shale plays. So in terms of uh, break-even prices, even ultra deep water plays are really competitive. I took this diagram from International Energy Agency. It shows the amount of CO2 emissions from operations, not fossil fuel burning, but from operations of the oil and gas companies. Again, North Sea, when we look at deep water plays in North Sea, Gulf of Mexico, etc., it has some of the lowest carbon dioxide emissions per barrel. This is 1 kilogram of CO2 emitted per barrel. So again, deep water wells are relatively better in terms of CO2 emissions compared to onshore or shale or even heavy oil, etc. I should also mention that before the shale revolution, really it was the deep water that was the engine for the growth of reserves and also oil and gas companies. I took this is a kind of dated slide. It comes from, I think, Offshore Magazine, 2005 or so. But the data comes from IHS. And basically, it shows that during this decade, 1993 to 2003, offshore, shelf, and deep water amounted for 65% of the entire discovery. And with deep water, um, you know, amounting to 40% of that. And considering that the deep water exploration, really the wave started in 1995 or so. So this was a phenomenal growth for deep water technology at that time. And even today, um, again, this data come from WoodMac. It was published at SP's JPT magazine. It shows that the global, deep water has added annually 13% growth rate. This is phenomenal. And in 2019, the deep water production passed 10 million barrels a day. That's like 10% of the global production. So all this data show demonstrate huge potentials for reserves growth in deep water, and especially in terms of giant fields. Currently, these 14 companies they produce more than 90% of deep water oil and gas. And most of them, I'm sure, familiar to you. Some of them are major international oil companies, some are mid-sized, and a few of them are national or state-run oil companies. Now, some remarks on deep water plays. This particular cartoon, um, uh, I think I found it like years ago, maybe more than 10 years ago or so, but it's interesting in the sense that deep water exploration, because it's deeper, because in terms of technology and also our access to petroleum systems, our knowledge of, insufficient knowledge of petroleum system. So it's a bit risky, especially considering that each deep water well, really costs tens of millions of dollars, sometimes even more than 150 million dollars. So it's a very expensive, very costly operation. So it's very important to put some science behind these operations. One of the things which would be very helpful is to consider the tectonic setting, tectonic framework of this deep water plays. Back in 2020, the COVID year, the lockdowns, I had more time to put some thoughts on paper, and I wrote this article, and I was trying to basically relate the Wilson cycle of opening and closing of oceanic basins to deep water plays. And I came up with this diagram showing different models, how the continents and the oceanic floor interact in terms of petroleum basins. So you have African model, a huge continent sitting basically sandwiched between two oceans. You have Atlantic model. It's a passive margin on both sides of the continent. Or Indian Ocean model, you have an active margin on one side of the ocean, but passive margin on the other side. North Pacific model, you have subductions on both sides of the continental margins, or Eurasian models, which is a bit more complicated, but here you have the continent really dominates, the continental part dominates the entire plate. Another exercise, again, these diagrams come from that particular article, is to view this deep water plays in terms of active margins versus passive margins. As you know, most of the deep water plays are located, or they have been explored in passive margins, on passive margins. But as some areas like in Indonesia, Caribbean Basin demonstrate, active margins should not be ignored, especially the four arc basins. Another thing to consider in terms of evaluating these deep water plates is the presence of these fossil rift basins onshore, what's called olocogens, which is a triple junction. Basically, you have a triple junction, and then two arms create the new oceanic floor, but the failed rift arm becomes a locus for sedimentation, but it does not become an oceanic floor. And in fact, they have huge impacts on the further development of offshore and deep water plays. Now at EGI, we have been studying offshore and deep water plays and basins for decades. In fact, I joined EGI almost 20 years ago, and for most part of my career at EGI, I have mostly looked at offshore and deep water basins. It's in the past 5 years or so that I have forayed into shale plays in North America. So these data are also interesting to consider. So about 876 sedimentary maps have been mapped. Almost 67% of those basins are coastal shelf deep water. So basically offshore basins. And only 290 of them are landlocked onshore. We are also looking at this deep water plays in terms of deltaic versus non-deltaic plays. Only 55 of these offshore basins they have modern deltas. So this is also something that we consider in terms of evaluating these basins. Now, there are about 1,200 giant and supergiant fields. 48 of them are located offshore. And this pie diagram shows the distribution of this offshore giant and supergiant fields. So you find almost, everywhere in the world. But the interesting thing is that even though 67% of sedimentary basins are offshore, only 40% of the giant fields are located offshore. So this shows that there is tremendous potential for giant fields in offshore and deep water basins. A new frontier for deep water exploration was really opened in the past 2-3 years with the discovery of Venus, Total Energies Venus field and Shell's Graph field, both offshore Orange Basin in South Africa. These are some puzzling plays because these are Cretaceous plays sitting directly on oceanic crust. So there are lots of questions about why what makes them work, what are the petroleum system factors that makes this, ultra deep water plays possible. And we are looking actually into this issue. It's very important. Some of the key questions are related to the continental margin, the nature of continental margin, the nature of the oceanic floor structures, the source rocks, where they are, and how because they are conventional, they are migrated oil and gas. So what are the migration pathways from the source to these traps? And also, what are the concepts? What are the really factors? Can we come up with a framework to evaluate which ultra deep plays will work and which ones will fail? This map, which was constructed by my colleague, Dr. H. Setoyama, shows the location of the wells beyond the continental, oceanic continental boundary. Basically, most of them are sitting on the oceanic crust. So there's a huge potential. There are lots of wells to study and to evaluate and to come up with some play concepts. Outcrops are very important parts of deep water exploration. Outcrops are, we can access them easily, and they give us tremendous amount of information in terms of both sedimentology, reservoirs, source rocks, and also structures. This map shows 5 particular locations that I have done field work during my own career, especially in the past 20 years or so. But there are many other outcrops and fields that we can study. And when you are doing, field work in this deep water outcrops, always you will come up with some surprising discoveries. And um, I will share one particular feature from this deep water sediments outcropped in Boso Peninsula in Japan. So you have a sand-rich, this grayish color, darkish color sand-rich um, rocks, and then you have mudstone below that. These come from close to thrust structures, so you have all these deformation bands in the sand-rich layer, but also these vein structures, these cemented veins in the mudstone. Um, Here, what you see is the thin section um, photographs of the deformation bands and also these vein structures. Um, the blue epoxy shows you the porosity, but as you see that both in the deformation bands and also in the vein structures in the mudstone, you have porosity collapse. You have lots of clay minerals and plagioclase, etc. So these porosity collapses, these features indicate um, they would really inhibit fluid flow in this type of rocks, the rocks which have been deformed in this way. Again, lots of, interesting features, you will find in this deep water sediments and the structures in, outcrop. Um, these are some areas related to deep water basins and places that we are currently working on at EGI. Guyana-Suriname Basin, we have completed a report. East Africa, we are looking at East Africa basins. Ultra deep water basins, I mentioned. And also my colleague, Dr. Setoyama, is leading this project on source rock pyrolysis kerogen organofacious evaluation by machine learning. So please contact us if you have any particular question related to any of these projects. Now, the fifth wave of petroleum is perhaps really the energy superbasins, especially in light of the energy transition and decarbonization efforts on the part of the oil and gas companies. Now, these energy superbasins, as I said, these are more integrated energy hubs with hybrid production. This particular diagram comes from a paper I recently published in First Break. Basically, it shows what are the components of an energy superbasin, whether it is onshore or offshore. Well, you have, of course, the traditional, oil and gas resources, but also you tap into any renewable resource available in the superbasin, mineral production from produced water or from seafloor, carbon sequestration, and microgrid electricity, so that you are independent, very integrated system in terms of your operations, and also contribution to the local environment in terms of decarbonization and local economy and local education and the workforce development. These activities are already happening, especially in Europe, offshore wind farms, hydrogen production from seawater or from natural gas fields in North Sea. And even in Spain, there is a project to use this floating photovoltaic, solar panels to produce offshore hydrogen. Tidal power, this is also something, I would say, a cutting edge technology. This particular project comes from Nova Scotia, Canada. Um, Produced water, produced formation water. This is the largest waste from hydrocarbon production, both onshore and offshore. So on a global, this is an average, global average for every 2.5 barrels. I'm sorry, for each barrel of oil that we produce or gas, equivalent gas, we produce 2.5 barrels of formation water. This is huge. So if you are producing 100 million barrels a day, which is what we are doing, currently, so you have 250 million barrels of produced water, uh, you know, each day, every day. So this is a huge, huge resource. And some studies shows that some of these produced waters, not all of them, but some of them are actually enriched in rare metals, magnesium, lithium, etc. So this is also something that I assume will grow tremendously in the coming years. And the seafloor itself, uh, there are great potential for metal production from nodules, from crust, etc. But also it comes with huge environmental challenges. We should not deny the environmental impact of the deep sea mining. What we are trying to do at EGI, this is a new initiative. We are trying to create an atlas, EGI atlas of deepwater superbasins as integrated basins. We have identified about 33 attributes and maps, input attributes into this database atlas. Um, I do not have space to list all of them, but these are the categories, geospatial, infrastructure, margin attributes, basement attributes, mineral potential, met ocean, both meteorological and oceanic currents, sedimentary and stratigraphic framework, petroleum system, and field sizes. So using this different attributes and maps, the output applications, really how we can use this atlas in this database, we can answer some of the following questions. The basin and the field longevity. We can identify the petroleum plays in terms of archetypes and variances. What elements really constitute the archetypes for petroleum plays, and what are the variables and to what extent? In terms of portfolio ranking and risking, companies can come up with advantaged exploration and production portfolio. We can identify the bypassed or ignored plays, and also the potential for non-hydrocarbon resources and decarbonization strategies in offshore and deepwater basins. Now I will change gears. I'd like to introduce a web-based global database which we have constructed at EGI. We call it ICORS Offshore. ICORS stands for Integrated Continent Ocean Database. This is a huge database. It can be used for both exploration, but also for carbon sequestration projects. We have been working on this, EGI has been working on this for over 12 years or so, and we have harvested a tremendous amount of data from various countries and basins and sources. The price tag is, it's an annual subscription. It's a web-based, Google Cloud-based analytic tool. It's $40,000 for companies which are not EGI's member companies, not corporate associate members, but for EGI corporate associate members, it's $20,000 per year. Um, these are just a few introductory slides. My colleague, Sir Thomas Cook, he will be giving a demo of iCords after my presentation, but I just wanted to highlight a few features. There are several data categories and lots of capabilities in terms of mapping, visualization, but also data plotting and data query. There are also lots of supportive maps, seismic maps, geophysical maps, which you can use to contextualize the geochemical or petrophysical data. There is a website. You can visit our website, and there's a form if you have any question, or if you would like to get more information to subscribe. If you fill out this form, it will come to us, and we will get back to you. I think this is my last slide. So I thank you very much for your attention. And my email is here. Please feel free to contact us. I will stop here. And now we will change. We will have a change of the crew. Tom, are you ready?
Yes, Rasoul, I'm all ready.
Thank you very much. So I will mute. Tom, it's all yours. Thank you.
Great. So I'm having trouble seeing my green line, but you should all see iCords offshore. Is that correct?
Yes.
Thank you very much. Okay, well, I'm kind of getting over a cold or something, so bear with me. My voice might crack a few times, but thank you for showing up and welcome to EGI on this morning. And I'll briefly go through the iCords offshore. We'll go ahead and log in. iCords is based on a vision that Dr. Sorkhabi had. Could we take pretty much all of the offshore and quite a bit of the onshore information and put it all in one place for convenience in order to make oil exploration easier? And so this is the current state of the application, and you know, we continue to develop it and make it better, but we'd like to show you what we have so far, and you can tell us other areas of interest that you might have. So we have basically just one web page. We try to bring the data to you instead of you going and getting the data. This defines the well search parameters, which I think we have about 100 different ways to look for wells and their geochemical samples. You'll pile up a series of filters in order to get through all the data. I think we currently have about 11 million measurements in here. And so obviously it's a needle in a haystack problem, which is really the problem. You can put the data in one place, but how can you find what you're looking for is always the big question. As you can see over here, we have a map of the world that our colleague Christopher Kessler has put together, demonstrate all the places where we currently have wells. But of course, this tool then goes into the earth, so I can't show you the 3 dimensions of it here, but you can see that we're very rich in offshore well information. And then after we do a query, you'll see the results down here in the record set. So let's do an example really quickly. In our first query, we'll say, as far as wells, I would like to know all of the wells that are in the basin, the northern North Sea. And additionally, I'm only interested in those cases where there's a geochemical sample where the total organic carbon is above 2. So those are the 2 filters. Now we're going to define what data we would like to come back. Now, of course, we'll find the basin and we'll get the TOC back since we queried on those. But I mean, we filtered on those, but then these are the ones that will return. So you'll notice we have many categories of data that's in the database. You can choose any one of them. In this case, we'll be looking through the pyrolysis, and you can see we have a healthy selection of pyrolysis information. I'll be selecting S1, S2, S3, Tmax, the hydrogen index, the oxygen index, and I think I'm also going to go over to the thermal maturity and pick out the average indigenous vitrinite reflectance. And so we're going to filter on these 2 things, but we're going to return those 13 things, and then that will define what is the return. This is a vast amount of data, so we do a little pre-query to see about what's going to come back. Usually takes about 5 seconds. And you can see that 2,000 rows are estimated to come back. So it's going to be a very nice, healthy query with lots of information into it. And if this happened to be over 10,000 rows, we would probably stop you at that point and say, please narrow your search down a little bit. But let's go ahead and begin the actual search. And this also usually takes about 5 to 10 seconds. And there we go. So it automatically goes into the area of interest in all the wells that fit that parameter. Now, there was 130 wells that, once again, are in the northern North Sea and have a geochemical sample somewhere that has a TOC greater than 2. And of course, here are our TOCs. You can see the one with the smallest value is 2.01, and the one with the largest is 78.7. And we can go ahead and put in a histogram and see that the grand majority of them, about 1,800 samples, are between a TOC of 0 and 8. But of course, the very interesting ones would be the TOC between 72 and 80. There's about 10 of those. So that's just a good way to get an overview of what we just searched. Searching back on well headers, my throat's starting to crack now. If we want to know more about a particular well, or maybe everything we know about it, we'll go ahead and ask for the full well information. And as you can see, this well is about 3,800 deep. It's got these samples. The particular one I just clicked on was this green one, but we can scroll up and down and get an idea. And this is very typical. Most wells are not fully represented. They'll just be a large blank space and then a kind of area of interest. So for this one sample, which we can see is at 3532.99 meters, we have this much pyrolysis information on it. We have this much thermal maturity on it. And we also have this total organic carbon. And interesting to note, thermal maturity was measured 3 times. This was the first attempt measurement, the second, and the third. And this sort of thing is necessary because geochemistry is just complicated, and people measure things a lot of times, so we have to take that into account. And then it's very important to us to always be able to say what was the data source of a particular measurement. And so in one click, we can go right back to who made the measurement, what the measurement was, and whatever other information you may be interested in. This iCords is a tool of convenience, putting all the information in one place, but as you can imagine, it's very heterogeneous. So that gives kind of a first query overview. I'll take a short break at this time to see if there's any questions before I do my second query. Okay, I'll go ahead and move on. So I'm going to clear out and begin the second query, which in this case will be interested in one of the places that Dr. Sorkhabi had mentioned, which was the Southwest African Basin. And I'll go ahead and try to put a little lasso around where I want to be, which will be on this continental shelf. And we'll stretch it basically from Angola to South Africa. Oops, lost it. There we go. And so that's Southwest Africa. That's our area of interest. And I think another thing we'll do is once again, filter on the amount of total organic carbon, which in this case, let's make it greater than 1. So in that entire area, what will we get back? $1,800 rows, once again, very good query. Let's go ahead and do that. And there we go, 23 wells with over 1,800 samples and 1,800 measurements within it. So that's great. The lowest TOC was this one, DSDP 4364, and the highest one was this one, 56.36 at DSDP 4361. So that's very nice. If you're curious about this area and what is sample depth versus TOC, we can plot that out really quickly. And so with increasing depth, we see some increasing TOC with some points of interest, such as here, where we can see which well that is, which sample and which depth, and what the TOC was. So very good. So let's give you an analysis of the overall area by doing a very special plot. Dr. Sorkhabi has really, I think, been interested in trying to make analysis as easy as possible. So for all those wells, we'll run through the pyrolysis TOC report. And here this lists all of the wells that were in that area. And you can see that we have histograms for depth, histograms for hydrogen index, histograms for oxygen index, etc. In this next one, we can see all the wells and we can see all their depths relative to each other and all of the samples. And if we wish to click on any of these and find out more about it, that's quite easy. But the interesting part is the next parts. For instance, the production index versus Tmax, we can see that these are kind of immature samples. We're not seeing much in the oil or the dry gas according to production index versus Tmax. And we've got 7 other analysis tools. So let's see what they say. This says the area is gas prone, not particularly oil prone. Here we can see kind of a different, well, no, once again, this says it's gas prone and less so than oil prone, although a lot more scatter in this particular plot. Here we go through on the types. I am not sure of 1, 2, 3, and 4, which ones are gas prone and oil prone. Oh, it's up here. Yeah, not as much in the oil, but once again, this one concurs. These are perhaps immature for oil production. And then coming over here, not so much in the oil, but oil, gas, and perhaps gas rich. So we see a rough concurrence among those. Vitrinite reflectance tends to be a little bit rarer, but we do have 2 here. Once again, concurrence, immature. And then on the vitrinite, once again, immature on these as well. So really, with just 1 query and pushing 2 buttons, we were able to get a rough idea for this geological area, what its potential for oil is. I'll go ahead and just give a space for any questions, and I'll quickly go through my next part. Okay, I'll go ahead and move.
I don't see any in the chat, Tom.
Chat?
I don't see any in the chat.
Okay, wonderful. Okay, I'll move on to the third part. Now, this is all public data from public sources, but it's pretty obvious people might want to put in their own data. So you can do that by coming up and saying, I'm going to upload data, my personal data, and it will be in a spreadsheet form. And there you can see that my personal data here about the Anderson Basin in the Northern Yukon, Northwest Territory areas, where I brought in my wells, I brought in what I know about them as far as their sample depth, and everything else is available. And then I can use exactly the same tools in order to analyze these samples. And so this is a very powerful thing. We know that you have your own private data and don't necessarily want to share it, but you want to maybe put it alongside the public data. And that's what we just did. Here's a bunch of public data, here's a bunch of private data, and we can do subsequent queries and see them side by side and analyze them side by side. And we think that's a very powerful feature. And then going on to the final part of my presentation, just want you to know that we have a healthy selection of maps. We know that seismic lines are extremely important. And so here we can see, I think what we have is about 15,000 seismic lines available. Clicking on any of them gives you the opportunity to download the actual seismic graph and then use it in your analyses. Oh, there it is. Kind of huge, so it takes a long time to come down. But we have a very healthy selection of these seismic lines available. And there are other maps as well for analysis. For instance, the ocean floor age. And additionally, say heat flow. And for any of these heat flows, we once again have a very healthy amount of information available. So that concludes my presentation.